Hello and welcome to section 3.4 notes. So we've been talking about first derivatives and what that tells us about our function. We know that the first derivative, if it is greater than 0, it tells us our original function's increasing. If it is less than 0, our function's decreasing. And if it's equal to 0 on an interval, our function is constant. We discussed the first derivative test. That first derivative test is going to let you figure out what relative extrema you have. What you do is you find your first derivative, you find your critical points by setting your derivative equal to 0 or undefined. Remember to be careful if you're finding critical points that come from where your derivative's undefined. You have to make sure that they are indeed points on the graph. Once you do that, you're going to look at your critical points. If you have your critical point here, to be a relative minimum, your derivative is changing from negative to positive, because that means your original function is decreasing and then increasing, which makes it a relative minimum. Okay, if we put that critical point on and we look at our derivative and we're changing from positive to negative, then that means the original function is changing from increasing to decreasing. It makes it a relative max. Okay, so describing a function. We've already talked about how the first derivative tells you about increasing, decreasing. It finds critical points. It helps us find those possible extrema. Well, the second derivative is also important to us. The second derivative tells us if the function is concave up or concave down. Now, why that's important is if we're talking about a function that's increasing, it's going to be important to know whether it's a constant increase, if maybe it's increasing but at a decreasing rate, or if it's increasing at an increasing rate. So we want to know the difference between these three increasing. So increasing isn't all of the picture we need. We need that concavity. Because if we're talking about stocks, we're talking about money growing, I want this guy right here, concave up as well as increasing. That second derivative is going to help us figure out concavity. It's also going to help us find points of inflection. Points of inflection, you can abbreviate that as POI. Points of inflection are where your second derivative is equal to 0 or undefined, but a point of inflection is kind of at the same level as extrema. To be a point of inflection, not only does your second derivative have to equal 0 or undefined, you have to have a sign change. So you have to be positive on one side, negative on the other side, your second derivative that is. Because a point of inflection is where your graph changes concavity. So here we go, second derivative. Concave up, you're looking at where your second derivative is positive. Concave up, people are positive, makes sense. Concave up, looks like that. Second derivative, if it's negative, you're concave down. Think about down people, they are negative people. Concave down, I know it sounds silly, but concave down looks like a frown. You get it. They're stupid, but the more stupid they are, the more likely we are to remember them. Now, where your second derivative equals 0 or undefined, those are possible points of inflection. There has to be a change in concavity for it to be an honest to goodness point of inflection. So let's take a look at what it's going to look like in our homework or on the AP test. They may ask us to find points of inflection and discuss the concavity of the graph of the function. They don't ask us anything about relative extrema, increasing intervals, decreasing intervals. So we will do our first derivative, but only because we need it to find our second derivative. So when I find my first derivative, the derivative of 2x to the third is 6x squared. And then minus 6x minus 12. The derivative of 5 is 0. There's my first derivative. I need to find my second derivative because second derivative is going to tell me about concavity and possible points of inflection. The derivative of 6x squared is 12x. The derivative of 6x is negative 6. The derivative of negative 12 is 0. There is no place where this is undefined, so I'm going to set that equal to 0. I find that we are equal to 0 at positive 1/2. Now I set up my little chart just like I did before, but remember this chart is only for us to keep ourselves organized. It does not in any way stand alone as a reason for our concavity change or points of inflection or anything. It's not part of our explanation. We put our little 1/2 on there, and then we're going to pick a point on the left, on the right to see what's happening with our second derivative. Well, if I put in a value like 0, my second derivative is negative. So on this side, our second derivative is positive. Okay. So when we're discussing concavity, just like with increasing, decreasing, you have to go through a derivatives explanation. We have to go through our second derivative. So I'm going to be writing my second derivative is less than 0 from negative infinity to positive 1/2. I apologize. Positive 1/2. So my original function is concave down on the same interval. Now I want to talk about where I'm concave up. My second derivative is positive from 1/2 to positive infinity. So the original function is concave up on that interval. I know it seems wordy to repeat the interval, but we have to make sure that we're explaining concavity through the second derivative, increasing and decreasing through the first derivative, relative extrema through those derivatives. Now, since 1/2 is a point on the original graph, and it is where I am changing from concave down to concave up, it is a point of inflection. And we will put, since f changes concavity at x equals 1/2, x equals 1/2 is a point of inflection. Okay. So our second example, when you get a function, it's always in your best interest to see if you can simplify that just a little bit. For instance, this is x plus 1 divided by the square root of x. That would be a quotient rule, but remember, you've got just one term in the denominator, so divide that. So that would be x to the 1/2 plus x to the negative 1/2. That makes finding your derivative just ever so slightly easier. We do have to go through the second derivative, so we might want to tighten that up and make that a little bit faster. When we find our first derivative, we're going to have 1/2 x to the negative 1/2 minus 1/2 x to the negative 3/2. Now we don't want to change any exponents because we're not done yet. We want to find the second derivative. So here we go with the second derivative. That's going to be negative 1/4 x to the negative 3/2 plus 3/4 x to the negative 5/2. Now we want to change our exponents. So we have 4x to the 3/2 plus 3/4x to the 5/2. We want to get a common denominator. It's just going to make things easier. Well, if we use 4x to the 5/2 power on the bottom, we only need to multiply this by x. So this by x and then this by x. So that gives me a negative x on top plus 3. Okay. Now, this is a good time to talk about those possible points of inflection, those possible critical points, everything involved in here. When I look at the original equation, I need to look at domain. I started with a square root. So already my domain was restricted. We were restricted to values greater than 0. Now normally with the square root we can have 0 underneath the radical, but because it's in the denominator we can't. So when I go to draw my little problem, my little number line here, I can't go past 0. So any critical point I have 0 or less than, I don't have to take that into consideration. Now remember, this is still representing the behavior of my second derivative. Well, if I set the denominator equal to 0, that will give me the critical point of 0, but remember 0 is not in my domain, so I don't have to worry about that. Look at where your numerator is equal to 0. That's going to be at 3. That is a point I can have, so that is a possible contender for point of inflection. You want to check a point representative in between 0 and 3, so say we pick 1. That's going to give us a positive on top, a positive on the bottom, so my second derivative is positive from 0 to 3. We're negative after that. We have to write our sentences. The second derivative is greater than 0 from 0 to 3. So f is concave up from 0 to 3. My second derivative is less than 0 from 3 on. So f is concave down from 3 to positive infinity. Before you move on to the next step, just quickly make sure that what you wrote down is what you wanted to write down. My second derivative is positive, so I'm concave up. Good. My second derivative is negative. I'm concave down. Good. Always just recheck that, because for some reason it just tends to change on us, or we're thinking we're on the next statement and we're still in part of the first statement. Those sentences are going to be very important, because that is our explanation, that is our justification of why we're concave up, concave down. Now f changes concavity at 3. At x equals 3, so that means x equals 3 is a point of inflection. Being a place where your second derivative is equal to 0 or undefined does not make you a point of inflection. It makes you a possible point of inflection. To bring it on home, you have to have a sign change. Positive on one side, negative on the other side. The next two examples are examples for you. So watch video 2 so that you can see if you've got the right concept. The last part of our lesson today is extrema and the second derivative test. What we did before was the first derivative test, and that is perfectly fine to find relative extrema. But there are certain cases where we might want to use the second derivative to help us find relative extrema. The way you do this using the second derivative test, you start off by finding the first derivative. You find critical points. Those critical points are going to be very important in the process later. Once you find your critical points, you find the second derivative, and then you put the critical point into the second derivative and see what happens. So if you put the critical point into your second derivative and it's a positive value, then you're a relative min. Okay, and that makes sense, because if your second derivative is positive, you're concave up, which is a relative min. If you plug it into your second derivative and you get a negative value, that means you're concave down, so that means you're a maximum. And that makes sense once you draw the picture. If your second derivative, once you plug in that critical point, you get 0, that means the test fails. You go back to using your first derivative test and looking at your sign changes. Now, just because of this down here, you're probably wondering, well, why would I ever want to use this test if it could fail and I have to go back to the other one anyway? There are going to be times where maybe all they give you is the critical point and the second derivative. If that's the case, you're going to have to know your second derivative test to get through it. Also, if your second derivative is not difficult to find, it might be easier to do it this way than to use your first derivative test. So on number 5 here, we've got our original function, and look at that. We have an x squared plus 3x minus 8. That is an easy, nice little parabola. When I take the first derivative, I get 2x plus 3. I have to stop and find my critical point. Don't move on to the second derivative yet. So my critical point is going to be negative 3/2. Label critical point, so they know what you've just found. Then I'm going to find my second derivative. Well, the derivative of 2x plus 3 is 2. Show them that you're putting in your critical point, but there's no x to plug that negative 3/2 in for. So it's going to be 2, which is greater than 0. So by the second derivative test, x equals negative 3/2 is a relative minimum. Okay. So just to kind of make sure we're all on the same page, we have to show them, we found the first derivative, we have to show them that it's a critical point by setting it equal to 0 and solving. Then we have to show them that we plugged it into the second derivative, what we found from that, and what that means to us in the extrema world. Okay. If they ask you what is that relative minimum, then we would have to plug this into the original function and find out what that y value is. That would be what is the relative minimum. Where is it? That's your x equals negative 3/2. So make sure you're reading the question very carefully to determine if they want what or if they want where. You've got 2 more examples to do here. So try them. Whoops, not that one. So you've got 1 example to do. The rest of your notes, just to give you an example here, you can look at this. This is where they give you information. You have to come up with a possible sketch that matches the information. Just kind of look over the information.